Hello, everybody. Thank you for joining us. I think a few people are still slowly joining in, so I'll give you some couple of minutes of grace. So today we have the first in our discussion series of the Safe Landing Climate's high-risk events webinars. We will be discussing cascading and compound shocks for food production, and we have three great speakers lined up for you. So we will hear three 20-minute talks from the three speakers that I'll introduce in a second. And afterwards, we'll have some discussion round. So in the meantime, while you're listening to the presentations, you're very welcome to start writing your questions in the Q&A box, and we'll go through them at the end. And if there is any technical problems, you can write also in the chat. And we'll keep an eye on that. So today we have, as I was mentioning, three very interesting speakers regarding this food production, cascading and compound shocks. Hopefully we'll go a bit more from the climate perspective towards the socio-economic impact perspective. And we'll have, a very good range of expertise in this. So first of all, we'll start with Corey Lesk, who's a postdoctoral researcher, in the climate modeling and impacts group at Dartmouth College, and he will tell us a bit about how compound streams impact crops and what it means for adaptation. We will follow it up with Franziska Gopp, who is a senior researcher at PIC, Postdoc Institute for Climate Impact Research in Germany. And she will tell us a bit about systemic risk and compound vulnerability in the food system with a special case study for Somalia. And finally, we'll have Peter Alexander, who is a senior lecturer at the School of Geosciences and the University of Edinburgh. And he will tell us a bit about how shocks related to the war in the Ukraine impact the global food systems. So as I was saying, 20 minutes for each presentation, and you're very welcome to start writing your questions in the Q&A box. And with this, I leave the floor to our first speaker, who is Corey Lesk. I hope you're able to share your screen as well. And thank you all for coming.
Great. Hello, everyone. Thanks for the invitation and thanks for being here. I'm going to talk to you about the crop production side of things with a focus on compound extremes. And when I mean crop production, I want to start by saying that I think crops are really the boundary conditions of the food system. And what I mean by that is that a good harvest does not ensure food security. Access, utilization, distribution is really important for getting food to people. But I do think that a bad harvest does increase food security risk. And so it's really the boundary condition. Crop production is the boundary condition. Lots of things happen inside, as we'll hear about in the other talks. But here the focus is on crop production, and a warming climate stresses crops in many ways. And when we're talking about compound extremes, the emphasis is really on the many, many ways. And the understanding of how climate and climate change affects crops has evolved a lot over the last 30 years or so. In the 1990s, the focus was really on mean changes. So what does +2 degrees globally mean for agriculture? So for instance, in the second IPCC report in the early mid-90s, extremes were not mentioned in the section on agricultural impacts. By the mid to late 2000s, there had been a huge focus on extremes and an appreciation of their importance. And this lasted kind of through the late 2010s. So for instance, the next IPCC report, the third one in the early 2000s, included the statement that projected changes in climate extremes could have major consequences. And so many IPCC reports pass, including dedicated chapters on the impacts of extremes, developed chapters on agriculture, but it's not until the sixth report in 2022 that we see the first mention of this new term, compound extremes, which encompasses a lot and is very important. And I think this turn towards compound extremes in the context of crop production is appreciating that under warming, crops are increasingly exposed to multiple stresses, and that those multiple stresses can have compounding impacts, but also that they can have their own distinct dynamics that are different than just one extreme at a time. And so I want to give you a bit of physical basis for why we have this strong expectation that warming implies increasing compound extremes. And you can see a lot of it in just this one relatively simple physical relationship here, which is called the Clausius-Clapeyron relation. And it relates saturation water vapor pressure to temperature. So in other words, the increase in how much water vapor air can hold as that air gets warmer. And you can see that it increases more and more steeply. So it's kind of this nonlinear increasing amount of water vapor that air can hold as it warms, around 7% increase per degree C. And this really means two different things that seem contradictory, but are really flip sides of the same coin. This means that a warmer atmosphere is a wetter atmosphere, but it also means that it's a thirstier atmosphere. So if air can hold more moisture, then when we have the conditions for some kind of precipitation event, like a thundercloud, then warmer air going into that thundercloud is going to deliver more moisture, and we would expect to have a more intense rainfall event on average. But the very fact that air can hold more moisture means that moisture must have come from somewhere, and that could come from the land surface, it can come from vegetation. This warmer atmosphere is also a thirstier atmosphere. It wants to pull more moisture out of crops. And so this relationship also implies more moisture stress. So we have this situation where under warming, crops are increasingly exposed to multiple stresses. A warmer climate has more heat extremes statistically, but it also has more hydrologic extremes, and that includes both more wet events and more dry events, and more increasingly co-occurring. I would argue that we understand the impacts fairly well of just this warming aspect and the impacts of heat extremes, but I think we are only beginning to understand this wider picture here, in which we have warming and more heat extremes and an amplified water cycle, more wet and more dry happening within the same growing season or at the same time. So the question is, how do these kinds of increasing compound extremes affect crop production? I'm going to focus on two kinds of events here. There's many kinds of interactions of stresses, but I'm going to focus on hotter droughts and how those might interact with more intense rainfall. And the short answer and the key message of this talk is that increasingly compound heat plus drought pose new risks to crops, and that these are only partially offset by an increase in intense rainfall. It's not entirely obvious that more intense rainfall would offset some of this, but this is what the data seems to show. But I think more importantly, starting to understand these risks and these impacts clarifies what we need to do to effectively adapt. So for the rest of the talk, I'm going to give you a quick introduction to the two main kinds of tools used for understanding climate and compound extreme impacts on crops. Then I'll give you a snapshot of these two results on hotter droughts and more intense rainfall. And then I want to talk a little bit to conclude about how I think this really informs what good adaptation looks like in crop production. So there are two main ways to understand climate impacts on crops. The first kind of family of methods is statistical models. And here we take, it's really a data-driven approach. We take climate data and crop statistics from the historical period. We bring those together into a data set, and we run regression models to try on that data to try to understand the crop sensitivities to climate. And you could build regression models that explicitly try to understand these compound stresses. And from those crop sensitivities, these are like parameters or coefficients, we derive some learning. We understand what these stresses do to crops. We can also take climate projections using those parameters and then project out future impacts that we'd expect in the future. The second family is process-based models, and this is really a complementary, quite different way to approach the problem. in which we start with our learning and we try to represent that in equations in a computer model, the key processes that are relevant. And then if we have those well represented and we run them in with climate projections of a future climate, then we can understand future impacts. I would say that in principle, this approach is the gold standard. This is how our climate models work. Our climate models are not regression models. They're physical models that represent the key processes. But I think in the case of compound extremes, we don't understand the key processes of compound stress, both in terms of what's relevant in the climate and what's relevant within crops and in the management system. So these factors are largely omitted from these models. And I think that's a big problem. That means we have blind spots about compound stresses in our understanding of future agriculture. So what I'm going to show you shortly is results that really are using statistical models to try to take that learning, which is an output from that process, and in the long term build that into the key process equations of these gold standard process-based crop models. So I'm going to show you now some results about hotter droughts and their impacts. And I want to start by showing you this data, which I think really clearly illustrates two key processes for compound heat and drought. So each data point here is a crop yield observation from around the last 40 years. This is just an example from Indiana, and this is for soybean. The coloring of the points shows the yield anomaly. So these pink values are negative, bad harvests, and they're situated within the space of soil moisture and temperature. So we have our hot and dry quadrant over here, increasing temperature like here, and drier as you go down. And so these are our really hot and dry events, and you can see that this is where we tend to see the concentration of the most severe impacts on yields. Critically, you can have a hot event like 2 degrees above average with normal to above normal soil moisture and see very little negative effect, pretty much normal yields. It's really only the conjunction of that heat with low soil moisture that gives you those really severe yield impacts. So historically, hotter droughts have had the strongest crop yield impacts. And I think this is indicative of those compounding between a lot of heat, a thirsty atmosphere demanding water from a crop, but at the same time, no water in the soil to satisfy that demand. So that's the first key process. I think you can see another key process here, which is there's this kind of like axis of variability down in this corner here, where, for instance, you very rarely see soil moisture levels this low without also seeing really high temperatures. And I think this is indicative of mutual intensification between heat and drought, the fact that those are not independent events, but they are physically connected. And there's a lot of complicated processes behind this physical connection, but I think you can summarize it fairly simply as the fact that warm conditions, high air temperatures, lots of solar radiation tends to dry out soils, evaporates the water out. All right, but then once there's less water in the soils, less water in the vegetation, then air can warm more above those dry soils. Because that incoming energy doesn't evaporate water. Instead, it just heats up the land surface. Right. So we see this mutual amplification between heating and drying that can make these events go together. Hot and dry tend to go together. What I'm showing you here is that stronger we expect stronger heat drought connections with warming. Warming actually makes this connection between heat and drought stronger. So there are two kinds of processes that make that connection. I'm showing you two of these, one above the other here. But the key idea is just that on each of these axes here, they moving towards these red colors and moving towards these purple colors indicates stronger heat and drought connections. You can see that those strengthening of those connections occur over most of global croplands. This is towards the end of this century under a kind of current policies emissions scenario. And this is the average across many models. There's a lot of uncertainty between models, but this is kind of our generic expectation. And what these changes are indicating is that these points are in the future under warming, not only shifting warmer, but shifting more into this kind of regime of strong heat drought connections. These kinds of connections that I think are driving this cluster of points here become stronger in the future. And I think that poses a risk. And we can actually calculate that risk by combining these historical relationships with these climate projections. And that way I was telling you before, this is one way we can use statistical crop models. And if you do that connection, then the calculation shows that future change in these connections between heat and drought actually exacerbate the impact of warming on crops compared to a model where you wouldn't consider that connection. It averages out to around 5% globally, which is considerable, but it's even greater in some hotspots like Southeastern Africa, which faces chronic food security issues, Southeastern Europe, which is geostrategically very important for the food system, especially for the Middle East and North Africa region, which is highly import dependent, and also in the central United States, a major grain producer and exporter. And in these places, the impacts can be as much as 20% or more. So globally significant and locally even more intense than that. And I would argue that this risk is not built into gold standard process-based crop modeling procedures that really inform our risk assessments of food security in the future, for a variety of technical reasons that I'm happy to discuss in a bit. So we see that hotter droughts have these intensifying impacts on crops under warming. And so the flip side of that is, if those hotter droughts tend to come also with more intense rainfall, will this help or hurt, right? Will that extra moisture delivered in intense packets be good and help overcome that, break that drought and deliver moisture when it's needed? Or will it flatten crops or cause waterlogging and cause a bunch of problems? So I'm going to quickly show you some results on this. I'm starting with the historical here. This is for maize and soy in the United States, where short duration rainfall data is available. And I want to highlight that this is the lack of hourly rainfall data is a big limitation in much of the world on trying to understand these impacts. So the insights we have are really coming from the United States here, which is itself a problem. On this axis is the yield impact, and I'm just going to show you two bars. One is heavy rainfall events, so heavy hourly intensity rainfall. And by heavy, I mean up to the strongest downpour of the year. So these are quite heavy events, but not the most extreme. And historically, those have benefited yields by around 3%. Now, there's also extreme events, and these are kind of relatively rare to very rare events, once every 10 years to 50 years to 100 years. So these are the strongest downpours. And that bar is right here, and you can barely see it, right? So historically, heavy rainfall benefits yields. The extremes are damaging, but they're very, very rare. So on average, they have this very, very small impact. Now I'm going to show you what if we kind of translate this model into a 4-degree warming. So understanding the impacts of that on the intensification of rainfall. And you can see that that medium blue bar here gets much larger in the future. We have positive effects of this kind of rainfall, and that rainfall increases in the future. And we can see also that those negative extremes, those really damaging events, become more impactful in the future, but the benefits of more heavy rain outweigh the damages from more extremes. And so if you add this up, then we expect yield gains from rainfall intensification, given that those really damaging events are super rare in the past and remain super rare in the future, even if they're slightly more common. So if we put these things together, hotter droughts are putting something like a global average minus 5% on crop productivity. More intense rainfall is partially counterbalancing that, which is a bit counterintuitive, but it's not enough of a counterbalancing effect to compensate for hotter droughts. So we have additional, this is just a highlight of the additional kinds of risks that are not really being considered at present in the comprehensive risk assessments. We're only beginning to understand and consider these risks in these assessments, but I do think that these really clarify what effective adaptation looks like. So I want to take you on give you a quick example of that. I think the key here is that we need multi-stress adaptation to climate change. So climate extremes are becoming increasingly compound, and in this context, some traditional adaptation approaches may not work very well. For instance, when we're breeding crops for drought, a traditional target that we're trying to improve in crops is to select genetics, select types of crops that reduce their transpiration during droughts so that they use less water, they decrease their water use, and they can maintain water status through a drought, maybe grow a little bit during a drought, but particularly survive until some rain arrives and those crops can continue growing. But crops also sweat. Transpiration is an evaporation of water from the inside of plants to the atmosphere, and that takes energy that now does not warm up a crop. So this is a lot like sweating. It's a bit different, but crops sweat in general. So training our crops to decrease their transpiration during drought may decrease a crop's ability to cool itself. So I would argue that this is potentially maladaptive as a target for increasing combinations of heat and drought. If we're training our crops to decrease their transpiration during droughts, that can boost the temperature of the crop itself, right? And so drought adaptation can amplify heat stress in this strategy, and this is a place where our drought breeding targets will be at odds with our goals for heat. But there are some alternative targets. So this is a really interesting example for soybean in some work that's trying to understand resilience for compound stresses. And some soybean varieties limit leaf transpiration during combinations of heat and drought. So in the leaves, they're saying, let's shut down moisture use and try to conserve water status. But these varieties maintain flower transpiration. And so the flowers are still sweating. They're still cooling themselves. That can result in 2 to 3 degrees of cooling of the tissue temperatures. And this is essential because those flowers are what are producing the seeds that we're going to harvest and eat. That's the food in this crop. And also those flowers are extremely heat sensitive. So I think this example shows the wealth of genetic resources that exist to breed for combinations of stresses and exactly what the strategy needs to be to consider these combinations of stresses. But there's a lot of problems with these genetic type solutions, right? Genetically plant-centric adaptations won't address wider food system vulnerabilities that we know exist, and then I'm excited to see the other talks that focus on this wider context. So for instance, are these technologies that are based on genetics in crops available to subsistence farmers? Well, historically, no, they have not been, mostly. And if so, they're often at the expense of food security, chiefly via the debt it takes to acquire these seeds. So as ever in the climate crisis, there really are no silver bullets. And I think so a general point is we need genetic adaptations that are holistic for stresses, but we need to be thinking about the wider food system at the same time. So thanks so much for your attention. There's a review that I led on this topic, summarizing a lot of these ideas, which you can find. Many collaborators there, many collaborators on this work. So thanks to them, and thanks to you.
Thanks, Corey. This was so interesting and also a perfect link towards this more towards socioeconomic impact. So I think I won't say too much on this. As I was mentioning before, please leave your comments and questions to Corey in the Q&A box. We have already a couple. I'll go through them after everyone's have presented their talk. And next we have Francisca. If you can share your screen, I don't know. If,
yes.
Yeah, great. Then I leave the floor to you.
Okay. Are you able to see my slides? Yes. Yeah, thanks a lot for the invitation. I will present today a study we have recently published with my colleagues Christian Webersack, and the study was led by my colleague Lisa Thalheimer about systemic risk and compound vulnerability in the food system, and a case study in Somalia. But before I dive into the case study, just to provide a little bit more context for this seminar, I thought I want to give a bit a background on the concept of systemic risk and how it entered in general the risk debates in academia, but also in the policy sphere. I guess you're all very well aware of this graph, of this figure, This is the classic figure used also in the IPCC and by others. Risk is a metric that consists of 3 submetrics, which is hazard, vulnerability, and exposure. And a lot of our risk debates and risk research focus on the hazard side, which is fine, but I think it's also really important to be aware that risk is not just relating to hazards, but it's also connected to vulnerability and exposure. And vulnerability is, for example, defined as a state of susceptibility to harm from the exposure to stresses associated with environmental or social change, and also the absence of adaptation capacity. And exposure was defined by the IPCC as the presence of people, species, ecosystems, and in general, the social and cultural assets that could be adversely affected. And this concept of risk that was used by the IPCC and a lot of others has over the time been also criticized and complemented specifically by systemic risk and the systemic risk lens. And here I have a study by Jakob Tscheichler and colleagues who published in 2018 a paper about compound events, where he points out that, and that was also basically mentioned by Corey in his talk, that the hazards are often compounding. Jakob Tscheichler and his colleagues, they combine specifically climatic drivers such as temperature and precipitation with the hazards such as droughts, and defined that as compound events. And with that, it was basically not the start, but it was one out of several papers focusing around the topic of systemic risk. And compound events is one characteristics of systemic risk. And there is, for example, the study by Jana Silman and colleagues who looked specifically, they did a literature review and tried to figure out all the different characteristics of systemic risk. In our Somalia case study, for example, we define systemic risk as something that arises from within the system as endogenous. Sometimes it's not even considered itself as a risk, and therefore it's not specifically tracked or managed. But it has a cumulative risk potential to negatively impact the overall system's performance and sometimes even lead to an entire system's breakdown. It has to be mentioned, though, that this systemic risk definition by the UNDRR is only one out of several. And for example, my colleague Jana Silman and her colleagues, they have used also, in general, the impacts as a definition of systemic risk. And as mentioned, they did this large literature review to try to determine common characteristics of systemic risk. And they found, for example, the scale, which can be all from local to global. It can be the relationship. So the common characteristics are the feedback loops. They're also sometimes called interactions, interconnections, interdependencies. And that really depends on the literature that you have, and different studies use different terms, that they all direct towards the interlinkages between different variables. System understanding was another pillar of the systemic risk definition, and that refers a lot to uncertainty. So you might have lack of knowledge about certain variables that determine risk, or they're just unknown or unpredicted or uncertain. And they also put in that category, they put the concept of tipping points, where it's not entirely clear when the system will reach tipping points. Another common characteristics are the transboundary effects. So what happens if the shock has hit the system? Then a key characteristic of systemic risk are the cascading effects. They're also called knock-on effects, indirect impacts, or ripple effects. Again, it depends on the literature what terms is used. And finally, the outcomes. And that is really often, like in systemic risk, the outcomes are system breakdowns and the collapse, and the failure of economic, financial, or social systems. It impacts the entire system. It's even called threat to system survival and unbound damage. But recently, systemic risk has also been used in systems and consequences where it doesn't lead to the entire collapse of the system. And I think my point that I want to make with this talk is also that the traditional risk definition has then been critically revised by all different communities, research communities, and they have added then the systemic risk lens to the traditional definition of risk. And I was involved, for example, in a study about drought risk led by my colleague Michael Hagenlocher, where we looked at the definition of drought risks. And you can see here the traditional exposure, hazard, and vulnerability boxes. We have underlying root causes, and then the interaction with climate and society. And then we try to combine that with systemic risk characteristics. And you see here in the hazard box, we have the compound effects that were really nicely introduced by Corey. The authors of that paper also divided exposure into direct and indirect exposure. And then lastly, the vulnerabilities, they also interact with risk and with the other components through feedback loops. So in terms of drought, that was the lack of coping capacity, ecosystem susceptibilities, lack of adaptive capacities, and exposure, direct and indirect exposure. In terms of food security, I published a paper looking at systemic risk in the global food system, rather from a conceptual point of view. And the main point I wanted to make with this graph was that the food system itself is not a fixed system that is only connected to production or only connected to consumption, but it's rather a system of systems. So the social system is interlinked with the economic system, of course, the biophysical system where it's produced, but also the financial system or the political system play their role. And I overlaid again the food system here with the systemic risk lens. So we had nonlinear dynamics, we have system interconnectedness. I mentioned compound events, for example, multiple breadbasket failure is a big topic where you have at the same time harvest and crop failure in different main crop producing areas. We have cascading events. A classic here is that you have drought that leads to increased food prices and poverty, and that might then lead to conflict, social unrest, and food riots. Or like referring to the uncertainty that were mentioned, ignored links or lack of data. And that paper was published right in the first wave of COVID. And here we had a major topic where the missed meals due to school closures, for example, also in the US. Okay, coming to the Somalia case study, what we wanted to do conceptually was we looked at the compound events that were investigated before. We saw that exposure was divided into direct and indirect exposure. And we said, actually, with the in terms of vulnerabilities, you could equally look at compounding vulnerabilities, because vulnerabilities themselves cannot be seen in isolation, but it's really important to look at how they compound. For example, we look here in the study, we look at environmental vulnerability, like land degradation or recurring extreme events. We have political vulnerability, like fragile governments or conflict, and socio-economic vulnerability with poverty and displacement. And we define in our study, we define compound vulnerability as driven by an array of systemic and interdependent stresses, such as poverty, etc., political instability. It's shaped by the complexity of drivers, for example, the organization of access to key resources, or how institutions then facilitate adaptation. And the same as systemic risk, compound vulnerability should be seen as dynamic in terms of temporal and spatial scales. And what you see here in our conceptual graph is we combine the compound vulnerabilities with systemic risk characteristics, as you see here around the compound vulnerabilities. You see the feedback loops, the cascading effects, compound events, etc. And what we conceptually used is that we see the vulnerabilities, the compound vulnerabilities, as the underlying issue. And then if the system is hit by a shock, the systemic risk trickle through the system and lead then to food insecurity, which is our endogenous variable. Maybe a little bit of background about Somalia. Somalia, since the 1990s, their faces enduring armed internal conflict, and you could really call it a war economy, including corruption, extortion, and the control of humanitarian aid, and with that also the guarantee for food supply. There are several violent groups that dominate the country, and the largest and most important one is Al-Shabaab, which is connected to Al-Qaeda, and they really led to a well-established war economy. But in addition to that, there are recurring extreme weather events. There was a large drought in 2011, but also from 2020 till 2023, they were facing a drought. And that linked to an absence of a central government, and coupled with poverty and civil conflict, it leads really to a severe situation in terms of food security, and also leads to large-scale internal displacement. In general, you could say that Somaliland in the north is more stable, and most food insecure people live in the south. There's a large drought reported displacement, for example, in 2018, which was then followed by flash floods, which again led to further displacement. And back in 2018, they did several surveys, and food insecurity was among the top 5 humanitarian needs mentioned in the surveys. In terms of livelihoods, the agricultural sector is really key in Somalia. It's also called the backbone of the economy, and the agricultural value added of the GDP was 65% in 1990, and in 2012 it was still above 60%. And like nomadic pastoralism is a key component of agriculture in Somalia, and that is connected to circular migration following the rainfall patterns. So Somalia has 2 rainy seasons per year, and the pastoralists then migrate. And that is again also linked to the recurring extreme weather events. So if you have recurring drought, the pastoralists their migration patterns are disturbed, and they have to go into land that belongs to other tribes, and that again leads to potential conflict. The data that we used for our analysis was a combination of field surveys and expert consultations. For the natural hazards, we used the disaster statistics, and then we had internally displaced people priority needs data, and of course, literature review. And in addition to the compound vulnerabilities, our methodological addition were the so-called systemic risk impact pathways. They combine the concept of systemic risk drivers with causal linkages between the vulnerabilities, and impact pathways as a concept existed already. Similar concepts are impact flow diagrams or outcome mapping. And we again added a systemic risk lens, and then introduced systemic risk impact pathways. They usually, when you design a study like that, you have characteristics that define then the boundary conditions of your study, and the 4 characteristics are the purpose. For us, that was, of course, to demonstrate how systemic risk exacerbates the environmental, socio-economic, and political vulnerabilities in Somalia, and finally leads and increases food insecurity. The model boundaries were Somalia, where we had then the data available. The time horizon is, as stated above, from the natural hazards from the 80s to 22, with then the field surveys from a limited time. And the level of aggregation was national, which can also be seen as a limitation then, that the surveys were conducted in 18 subregions. Okay, looking at the result, we see here in blue the political vulnerabilities, in green the environmental vulnerabilities, and in red the socioeconomic vulnerabilities. And the yellow variables are the external drivers and underlying root causes. And as you see, it's not just a traditional impact pathway graph, but we added the systemic risk components based on the literature review and on the data we had. And I will not go into detail in the entire graph, but I'll pick out a few examples. So we have here, for example, I don't know if you see my cursor, but we have here, okay, great. We have the vicious circle between political instability, armed conflict, and weak institutions. And we have here really a feedback mechanism that deteriorates further the entire political situation. And that might mean, as I have mentioned already here, in the socio-economic field, as a socio-economic vulnerability, the limited movement possible for pastoralists due to conflict and disruption of traditional circular migration patterns. And that might then lead to youth unemployment, which we all know is then very easy for violent groups like Al-Shabaab to recruit more people. So the recruitment by military strong elites, including Al-Shabaab, increases, which in turn then increases further the political instability and the conflict. If we come back here to the pastoralists who cannot use their traditional migration patterns, that might also lead to the livestock dying. And here we have, for example, the systemic risk characteristic of tipping point, because they don't, they might, if the drought and the weather conditions deteriorate, they will, like if the tipping point is reached, they will suddenly then, they will die. And that then means risk to the livelihoods of the pastoralists and lead to poverty. And then poverty might lead to rural-urban migration, but not as a direct consequence, but there are always lags and delays. For this paper, we have picked out two examples, systemic risk impact pathways that are shown here. And we had quite a debate with the reviewers in terms of how clearly you can link colonialism and market liberalization with the political instability. And the literature that we found and that we argued with was that the export-oriented colonial agricultural production was meant to extract the local resources and to meet the demand of the global north, rather than to look or to achieve food security and prioritize food security in Somalia. In addition, research and development was neglected. And what I also thought was an interesting argument is that colonialism undermined the traditional social structures, for example, the trust in traditional leaders in the communitarian Somali tradition. And with that also led, of course, with delay again, to political instability and conflict and weak institutions. This here led then to the collapse of state power and moved to into war economy, which is then a socio-economic vulnerability, the degradation of wealth over time, which increases poverty and in the end leads to food insecurity. The second example that we picked out as a systemic risk impact pathway is the increasing frequency of droughts and floods, which not directly, but with a delay, leads to land degradation, specifically here in Somalia to vegetation loss, which then reduces the food for the livestock. And in general, soil deterioration also leads to lower productivity in the agricultural sectors. And this is where the environmental vulnerability is then connected to socioeconomic vulnerability through rising food prices, again, poverty and food insecurity. Lastly, to end, what are the suggestions how the systemic risk can be managed? And the suggestions we found in the literature is anticipatory humanitarian action, for example, forecast-based financing tools can reduce vulnerability. And there is a suggestion from Mongolia where the provision of climate-resilient feeding, veterinary care, and water supply helps to prepare the vulnerable people. And it's possible to build or increase systemic resilience through social safety nets. That could mean cash transfer, school feeding programs, specifically for the vulnerable population. And of course, emergency crop and livestock asset protection. And with that, I'm at the end of my presentation. Thanks.
Thanks, Franziska. You really highlighted this cascading and interconnectedness issue with the whole problem. So this is also very relevant. So again, leave your questions for Franziska in the Q&A box. There's already one or two there for her. And then we move to our last speaker of the afternoon, Peter. Yes, I give the floor to you.
Thank you very much. Can you see my slides? Yep, great. Okay, thanks. So I'm going to be talking about the war in Ukraine, if you like, as a case study to some extent of this sort of cascading risk impacts of the food systems in a global context. I'm going to start by talking about the portrayal of the implications of the war in Ukraine on the food system. In the public media sort of policy debate, if you like, and then I'll come back to that at the end as well. But in sort of the core part of the presentation, we'll really be presenting some modelling work and looking at scenarios related to that conflict and the consequences of that conflict, and then sort of ending with looking back at sort of a reflection to see whether some of the portrayal in the media and policy debate is kind of reflected in the outcomes that we see in the modelling. I guess it's interesting that kind of all three of the speakers have talked about this in different ways, I suppose now. But I wanted to highlight, I suppose, that it's very much a food systems view that I'm taking here. So it's much broader than just thinking about food production. Obviously, we have lots of different systems, as we've just been hearing, that all interconnect. So as well as climate and extreme weather events changing food production, we've got people choosing what they're going to eat, which are responding potentially to changes in preferences, changes in incomes, and also changes in commodity prices. So there's sort of that food demand, social systems there, and obviously prices and trade and processing and exports and all sort of economic systems. And they're all framed through political, geopolitical aspects with and having dietary changes, having health consequences, which I'll talk about in some length. And clearly we could have risks that are occurring kind of in any one of those systems, or sort of starting in any one of those systems and cascading through to any of the others, and sort of and compounded with others, other shocks that are occurring through that system. So we're looking at this fairly holistically, I suppose, or at least attempting to as best we can. Obviously, the complexity is quite extreme. But coming back to the war in Ukraine, obviously we have the invasion in February last year, and there was a sort of a build up to that in the sort of preceding months, years, in fact, since the invasion of Crimea. But in terms of how that's been portrayed, as I say, in the media, I think you would agree that most of the portrayal has been around grain in sheds and sort of shipping through the Black Sea, which is why I chose to include that photo there. But if we, to pick up a couple of the quotes I've put on this slide, Russia and Ukraine produced 30% of the world's wheat supply prior to the war, and Ukraine is seen as the world's bread basket. Is a sort of a fairly typical framing of the significance of Russia and Ukraine in the global food system. I'll come back to that exact quote towards the end of the presentation, but for the moment, I think what I would highlight or agree with, if you like, is that roughly 30% of wheat was previously, in 2021, for example, exported from Russia and Ukraine together, and that's obviously substantial. And some countries were even more exposed to those exports. For example, North Africa, as well as some countries in sub-Saharan Africa, for example. And a lot of that trade was going through, the vast majority was going through the Black Sea, and there was a blockade of the Black Sea, as I'm sure you know. And then there was this Black Sea grain corridor agreement in place for quite some time that then lapsed. So, there's definitely been, large issues with maintaining that level of trade. And indeed, Russia is under sanction from the EU and US, for example. And although food and fertilizers are explicitly excluded from those sanctions, there's still potentially been issues with those exports related to sort of payment systems and insurance and things of that nature. So yeah, I think the point here is that the primary focus has been on the constraints to exports from Russia and Ukraine of food. However, the other aspect, which is also clear and is talked about to some extent, is the impact on agricultural inputs. Clearly, there was a huge spike in energy costs, natural gas particularly, but also oil prices. And as I'm sure you know, that Haber-Bosch processes uses natural gas primarily to produce inorganic nitrogen fertilizer. And that also saw a big spike in price, tripling in the 12 months to May 2022. So big increase of inputs costs there, as well as higher costs for machinery and transport, for example. Exactly how much of those impacts are directly related to the war in Ukraine is more questionable, of course. So in terms of this work, what we were trying to do was to sort of ask the question, what the relative importance of some of those drivers for some of the outcomes. So we have this disruption to trade, we have these higher input costs. How do those aspects relate to the changes in farmers' decisions about what levels of intensity to use, what crops to grow, etc. But and then how do all of those things flow into food prices and changes in international trade, and what consequences does that have in terms of diets and what people are choosing to eat or able to eat, and then how does that impact on human health? So sort of cascading effects in those terms, and how what's the relative importance of those different drivers for some of those outcomes. And that's in order to try and understand that, we really need to do some sort of modeling to try and sort of unpick and tease out some of those relationships. And that's what we'll be presenting in the next 10 minutes or so. So in this particular case, we use an existing model that we kind of had off the shelf, we've been developing for quite some time, called LandSim. And you'll be happy to hear I'm not going to talk through this diagram in great detail. But I'll just highlight 4 kind of major areas that are sort of contained within this model. We have a sort of a food demand module, if you like, which responds to prices and income levels and so forth to look at what people's diets are. We have sort of land use, sort of spatially land use decisions about what crops to grow where, what level of intensity to use, and we actually combine that with LPG gas, which is one of the models that Corey didn't mention, but I think he maybe was thinking of in terms of a process-based vegetation model. And there are others, but we happen to use LPG gas. It looks at the crop dynamics based on climate and other inputs, and then we have the sort of international trade component. But I don't have time to go through this in the model in too much detail, so I'll just sort of leave that there and present the results, if you like. So in terms of driving this model, what we needed to represent what within the scenarios, what scenarios we were going to test to shock the model with, that sort of tries to represent different aspects of the war. And so we chose these four scenarios. One, a no shock scenario where the sort of 2021 conditions kind of continued into the future. And then sort of the alternative one where we have both an impact on sort of curtailment of exports from Russia and Ukraine, and as well coupled with higher energy prices. And then 2 others which have only one or other, but not both of those aspects. So in terms of the curtailment of exports, we sort of Monte Carlo ensemble sampling, if you like, for this and other parameters, where we sort of had between 50 and 100% of restrictions from those exports. And in terms of the energy price, fertilizer price scenario, we had a tripling of fertilizer costs, which was consistent with the market conditions at that time, more or less, as well as a sort of 50% increase of sort of mechanization costs and transport costs. So these scenarios were designed about May 2022, and that's the data that the fertilizer price data at that time, and this kind of the conditions that we are simulating through these experiments. And the consequences of running those simulations are kind of in terms of the prices for different commodities within the model are shown here. These are the global market prices. And what you immediately notice is that, at least with this fairly extreme scale, that the export restriction shock shows relatively small changes in prices relative, at least to the scenarios which include the energy price component in the shock, where we see a sort of more or less doubling of prices for many of the commodities. And there's a range of different outcomes there. We could also look at this in terms of the total cost to the sort of the world food basket that's consumed. So this is looking kind of across 2 years between 2021 and 2023. And what it's suggesting is, if we look at the bottom row here, that roughly a 3% increase in the total basket of foods consumed globally under that export restriction shock, 2.6% is written there, which is actually consistent with a couple of papers that have been published since this one, but which would in some other senses be quite a large number, but when compared to the implications from the higher energy prices that are tested in this scenario, is obviously quite, is relatively insignificant, with a sort of an 80% increase in the total costs of food, assuming those the assumptions that I very briefly outlined. Now, the consequence of those higher food prices feeds into sort of nutritional or to diets, and therefore nutritional outcomes. So people will respond to those higher food prices by moving away from sort of discretionary consumption in the model towards more subsistence diets. So that would involve, less consumption, less overall, but also move away from discretionary products like meat and fresh fruit and veg towards staple commodities, and that has a range of health implications. So obviously the people will become, the body mass sort of range will change, but there'll be more underweight people as well as fewer overweight and obese people, and also changes in consumption of meat and fresh fruit and veg have other implications for health. So red meat is associated with a number of negative outcomes, and fresh fruit and veg positive ones. So reductions have changes in sort of, for example, cardiovascular disease, colorectal cancer, other forms of cancer, and diabetes. And we're using epidemiological relationships. We're able to estimate, based on those changes, the number of deaths that are either avoided or additional based on those changes. And unsurprisingly, unfortunately, the poorest in society tend to suffer the most. And obviously, there's a disproportionate number of people in sub-Saharan Africa who would become more underweight under those assumptions and lead to greater rates of death. So in terms of to give some numbers around that, there's some 60 to 100 million of people additionally undernourished under those scenarios, with 400,000 to 1 million of additional annual deaths based on net deaths based on those assumptions. There are also, unfortunately, there would be some environmental implications. So as you might expect, if we increase fertilizer prices, you would get a response to using less fertilizer, which is shown in the bottom left-hand corner graph. And then kind of over time, to some extent, you get a shift to other forms of inputs. So you would use more irrigation to sort of try and increase yields that way, but also more cropland area to expand to sort of compensate for the loss of productivity through that lower intensity. which consequently has an impact on the availability or the area of natural land covers and forests, with which would have consequences for biodiversity loss and soil carbon, for example. Because this is a spatial modeling process, we can look at the results spatially as well. And again, we can see that fertilizer use decreases very broadly. Again, as you might expect, it's interesting that the model chooses not really to abandon much land, agricultural land in Russia and Ukraine in response to these shocks, but instead lowers the level of sort of other intensity as well as fertilizer intensity. So it's kind of using the same amount of land, but using it less intensively. So just to sort of try to go back, if you like, to where we started to some extent, I think some people are potentially surprised by those results, suggesting that the impact from the energy costs, fertilizer costs, is much more significant than the loss of exports. Perhaps surprised by the sort of limited consequence for those loss of exports. And I think there's some. I'm going to give you 3 reasons why I think it may be correct what the model's doing in this case, and why also to some extent I think the portrayal in the media is often a little bit flawed. So I'm going to come back to the quote before that Russia and Ukraine produce 30% of the world's wheat supply, and suggest that's just plain wrong. Because it doesn't take into account the fact that there's domestic production and consumption of wheat. And indeed, most of the time, I mean, I'll be a little bit unkind taking that quote, because most of the time they get it correct, and they do say 30% of global exports, or something that's technically correct, but it's sort of portrayed in a way that I think is somewhat misleading, or at least partial. Because actually it's something like 75%, 76% of wheat is produced and consumed in the same country, so isn't part of those global markets. And if we want to give a number that kind of gives the significance of Russian and Ukrainian exports of wheat, say, to the rest of the world, it would be fairer to look at how much of the wheat that's consumed, for example, by the rest of the world that comes from Russia and Ukraine, i.e. that takes into account the domestic production and consumption in the rest of the world. And actually that would be a number sort of below 8% in wheat. And if we think about it, cereals overall will be something less than 4%. And so that kind of, I think, would be a fairer number for the significance of Ukrainian and Russian exports in total prior to the war. So I think that's at least part of the reason why, for that surprise element of surprise, or sort of and the second couple of reasons are sort of stocks and the ability to take for substitution. So stocks, there's substantial world stocks for staple commodities such as wheat, because they're relatively easy to store. So if we think of the stocks held globally and look at it as sort of multiple for the losses from Russia and Ukraine, actually we would be able to buffer those exports for approximately 5 years. Now, maybe that 5 years is perhaps unreasonable, but it does at least show that there's kind of ability in the system to absorb those shocks for a year or two, and allow the system to adapt and sort of in various different ways. And this is sort of what's happening through the simulation. And in terms of substitution, obviously we have substitution, dietary substitution of what people are choosing to eat, but we also have substitution in the system related to other uses of cereals. So in terms of wheat, obviously, well, most cereals, all cereals in fact, but particularly wheat and maize, there's a lot used for animal feed, as well as other uses, effectively bioenergy, and that gives us also further scope to sort of substitute within that system to absorb some of those shocks in different ways. So just kind of more or less beginning to wrap up. If we think about what's happened in the last year, or nearly a year since some of this work was published, obviously the shock has very largely more moderated to a great extent. Energy prices have come back to something more akin to their levels over the last 5 years, going up slightly more recently, but yeah, there's definitely been a big sort of reversion, if you like, and similarly for food prices, particularly for the sort of cereal crops, are back to a level quite similar to where they were at the start of 2021. There are some examples that you could argue there's a form of cherry picking going on here, but I've chosen to also plot chicken and sugar, where prices are substantially higher, but arguably there are, I think there are good specific reasons that are not related to this particular event why those two commodities are showing much higher prices today. In the work that we didn't simulate a reversion of the shock, partly because we didn't know when it was going to be, so we just assumed it continued forever rather than having to make some further assumptions. And obviously, when that would get removed, there would be some reversion in outcomes as well as some path dependency. So, sort of wrapping up, I think it's quite an interesting example of a shock, a geopolitical shock in this case, that sort of triggered economic shocks and with consequences all the way down to human nutrition and health. Yeah, I suppose that the next point here is saying we need to think about, when we're thinking about resilience and thinking about shocks and cascading risks, we do need to think, I think, quite broadly about where they, the different areas, different systems that could be impacted. Yeah, to reiterate, I suppose that in this particular case, I think that there's more negative consequences from energy price rises, but then the loss of exports. And my view, which is that the media does tend to like something that's easily communicated and kind of you can take a photo of, and sometimes the more indirect impacts that are harder to explain, even though they may be more important, can get overlooked as a result of that. And the final point here is that when trying to work on this, it was quite frustrating that you can produce the results perhaps relatively quickly, depending on in this case, but getting it published in sort of academic journals is a slow process, as we all know. And when you're sort of chasing a current affairs issue, that can be quite frustrating. Thank you.
Thanks, Peter. This was also very, very interesting. I especially found so relevant how you highlighted, this local effects were quite much smaller than we might have thought compared to the global, cascading shocks maybe of like the fertilizer use changes and energy prices. So this really brings into, to the foreground how this connectivity and cascading effects through the systems are so important to consider it. So I invite you all to post some questions also for Peter in the chat now that you have some time to mull over this interesting talk. And I'm going to start with a hard-hitting question by Kai Kornhuber, related to all of you, maybe, which, it's very hard to pose, but I will try to do my best. So what is your feeling or your thought in this balance between having a model that is simulates everything, or is able to simulate, to the best of our knowledge, everything, versus this much more, observational base, going to the places and identifying, the most relevant risks, hazards, or approaches. So where do you think is the limit here? Are we as natural scientists supposed to, fill every little detail in Francisca's diagram, for example, a priori, or are we bounded to actually see disasters happen in real time and then, fill the graph with whatever happened? So maybe since I mentioned you, Francisca, my name, you can go ahead and start off, but I'm very interested to see both of Corey's and Peter's perspectives as well.
Yeah, I also look forward to hear from Corey and Peter what they would say. But yeah, thanks, Kai, for your question. And of course, yeah, it's a good question, right? Like, not just what is our responsibility as natural scientists, but or quantitative modelers, but also in how far are we able and should we model certain maybe more qualitative aspects such as vulnerability. And I would say, to be honest, my tendencies goes more and more as a traditionally quantitative modeler. I think more and more that the important questions in terms of how society should react and how we should improve disaster risk preparedness, I think the actual really important part is the qualitative data. And I think the quantitative data is really good for risk in terms of hazards modeling. But if the question is how should we react as society, then I think qualitative data is really important. And my personal opinion is that we have to be careful to not reduce and quantify or simplify some really complex qualitative topics and issues, because I think if we're too reductionist or we just use national data and don't look into the context-specific information, we might really miss important links and might conclude or come to the wrong policy recommendations. So as a quantitative modeler, I would say qualitative data is really, really important and maybe should not be modeled by us always.
Thanks, Franziska. Peter, do you want to pitch in next?
Yeah, I can go next. I mean, I could answer the question by saying, you know, or the question almost could be rephrased as why model? To some extent, and of course there isn't an answer to that. There isn't an answer to that. There's many answers to that, and you know, the answer is not usually predictiveness. I mean, okay, when you're generating a weather forecast or something like that, then there are some cases where it is, but it's not the standard answer, or it's not the answer where the timeframes are very long and the uncertainties are very high. So in those cases, such as what we're talking about today, the reason why we're trying to model it, particularly where it's quantitative, isn't really the numbers themselves. It's the understanding that we get from the model behavior that we didn't understand before. We have to be careful not to be seduced by the numbers, because we are getting, you know, exact values, and it's very easy to get sucked into the well, the model's right, and you know the answer's 42. Yeah, we need to not do that. We need to keep this sort of qualitative view. But as I say, most of the modeling I do is not to get the number; it's to get the insight into some of the dynamics and some of the behaviors, and that insight is largely more qualitative. But we're still using numbers to get to that qualitative insight, and yeah.
Yeah, I totally agree with this, you know, both perspectives, that often, you know, what we're interested in is qualitative. Numbers can be useful. And I mean, in a lot of the individual risks or components of risk systems and connected risks, people are trying to model them quantitatively. I mean, there's a whole field of quantitative social science that is interested in qualitative outcomes, but puts numbers to these processes to understand their dynamics, right? Not to deliver correct answers, but to understand that there are differing sensitivities across the chain of processes, and that the values of those sensitivities ultimately determine what's important and what you should be paying attention to. But I mean, we're talking about vulnerability and disaster risk reduction and correlated risks in the context of climate change, where the, you know, and you know, as we have insights that lead to policies, there are going to be questions of then who pays for the policies, who pays to implement these kinds of common sense things that we can reveal by just trying to understand the systems. And we're in a situation where there's an unequal responsibility for climate change, borne unequally by people who haven't caused it. And that's a values judgment, right? That's a fundamentally qualitative thing. So in this context of loss and damage, and the fact that mounting compound climate risk is there's liability there for those damages, or people who are responsible. I mean, this is one element of a political dimension that can never be addressed really quantitatively. It's a matter of international law and political consensus. I do think numbers can be useful for things like that. There's a lot of quantitative research going on showing how much of impacts are attributable to specific emitters, international companies that are in principle liable for those torts. So numbers still play a role here, but I mean, again, fundamentally, the insights have to be qualitative. I agree there.
Thank you all. This was really good answer. I was also wondering, so you've all to some degree mentioned this, different models that we have right now, like Corey even mentioned this gold standard, right, of, what we think is best. But we all agree that, I mean, that's pretty far away from a gold standard at this point. Like we're still, working on including all of the relevant models, especially mechanisms, and especially how they interact with each other. So I wanted to ask you also to all three, what advantages or what ways forward do you see right now of including this compounding, cascading effects better in all of the type of models that you use right now? Do you see breakthroughs coming through in the next years, or do you really don't see a way that is going to be improved with the knowledge that we have right now? I don't know who wants to start. Maybe Corey, now that I mentioned you by name. Maybe you want to go ahead.
I can start by not answering the question, if you like, which is always a good place to start. But sort of adjacent to, maybe it is answering the question. Anyway, you talked about the gold standard, quoting Corey, and I like that. I think it's maybe it's too much. It sounds like, but I completely agree. Process modeling, which is fundamentally likely to gain more insights. See previous answer, and capture more and tell us more, and also work outside the scope that we have empirical data for. And particularly when we're talking about extreme events and cascading risks, we're likely to be moving outside of what we have good data for. So therefore, it's even more important that we sort of use empirical data as much as we can and get as much richness and insights as we can out of it, but start having process-based models. And I think it's also, I completely agree with what Corey said. The climate models are good at that. The plant crop models, I think, are not bad at that. But the social models are really rubbish at that, because we don't really have good insights into the processes, number one. But number two, in related to this area, integrated assessment models would be the kind of the biggest game in town, and they don't even try and have processes or human processes. So everybody would adopt something as soon as it's become economically rational to do that. And we know that's not a good representation of of social processes, even though we don't really know what a good one might be. But it's definitely not that one. So we need to do better in trying to model those social processes as processes rather than something else that we know is flawed.
Thanks, Peter. This was really very to the point. I don't know if Corey, Francisco, did you want to add something to this? If so, go ahead.
Sorry, go ahead.
Francisco, go. Okay.
Sorry, I should have done better.
I mean,
Francisco, please go ahead.
On the
Or Corey, yeah.
Sorry. I'll just go. The process-based crop models, I think they're actually, are opportunities to make them better. So, they are pretty good. I agree with Peter on that, but I'm not sure they're good for the right reasons. And there's a lot of parameterized relationships there. So things where we really are just applying statistical fits to historical data. And that raises questions of whether they are representing non-stationarity, whether they are representing, regime shifts in physiology related to climate. And a key one there is CO2. CO2 totally changes water relations in crops, and how that's built into models is somewhat based in theory, but there are a lot of issues there. So there are ways you can improve it, but again, when we're talking about the biophysical carbon water optimization of a plant, it's a very small piece of the food system. So I think there are places where better process representation can be done and would probably help. And that can extend to some extent to dynamics of, for instance, food stores, strategic reserves, and things like that, where, you know, there already are partly governed by economic models and risk models, trying to calibrate food reserves, although they're constrained by the political reality that determines how they're used. You could try to fit those things together, and I think, you know, there's a lot of work on how to model past the biophysical, and bridge that. And I mean, things like these Monte Carlo global variance assessment across models, I think, you know, again, doesn't give you the definitive answer, but does constrain kind of what the important processes are. I totally agree that people don't listen to scientists, people listen to some combination of all kinds of messages. And here's, I think, place where I think, like, the idea of real-time science, which is, I think, in the climate sphere, is increasingly important. Blog posts, preprints, people who discuss scientific results outside of the normative peer review mechanism could be a really powerful and increasingly important thing here, where we say, we're part of the conversation, we need to be part of the conversation in real time. And that doesn't mean that everyone should just listen to us, but take what we have to say, at least.
Yeah, I also agree with what Peter and Corey said. And I would add, again, it depends on the question, right? Do you want to, if you focus on the modeling and you want to improve or make the models more complex, and then in the integrated assessment models, they more and more try to include behavioral data and behavioral variables, or the entire sector of agent-based models is getting more popular because they are able to include human behavior. And then in terms of combining quantitative and qualitative work, also what Corey said in terms of the future that is not stationary, so we cannot use historical data to project into the future. And there are a lot of new methodologies, qualitative methodologies like foresights or future visioning, where people in creative workshops design possible futures, and then the quantitative modelers try to reduce them or try to pack them into quantitative future predictions. But I would say, again, it depends on what you want to solve or what the question is. And I think there are also really cool innovations in terms of social technologies with new participatory methods. I think one of the questions in the chat was also, how do you include indigenous or local knowledge? So I think it's really important to not quantify everything, but to search also for different sources of information, different types of knowledge, search for traditional practices and learn from them. So I think it's really a lot of innovations and a lot of learning on all sides, from the modeling, but also outside the modeling going on.
Thanks. There's another question, also very hard-hitting, by Leo Bosch in the chat, and Gabi Hegel also added some comments, and I'm going to try to summarize it as best as I can. So the question goes towards, you know, there are so many uncertainties from the climate scenario we might end up, you know, in, towards, you know, how the human system will react to whatever happens and everything in between. So from your corner of science, which of these uncertainties are the ones that are worrying you the most? And do you think, you know, that the projections to the future can be trusted at all? In which direction do you think they're biased? I mean, I know this is a $1 million question, but I'm sure we'll benefit from your insights on this a lot. And maybe, Peter, do you want to start?
Maybe. Yeah, so where is the uncertainty greatest? Yeah, I mean, I suppose the projections are just that, or the scenarios are just that. They're scenarios. They're not predictive again. They're, you know, they're a storyline. There's a narrative. You know, if we think of the SSPs, RCP, you know, they're a narrative that's trying to frame the plausible futures to some extent, or, you know, bound them. Are they extreme enough? Do they possibly not? Maybe they're slightly too optimistic in general, and they don't consider extreme events. I don't like the phrase black swans, but, you know, I'm going to use it anyway. Yeah, so I think perhaps where we've been to this point a little bit narrow in terms of a lot of the sort of scenarios that we're representing. Yeah, I mean, and there was also a mention about CO2 and CO2 fertilization a couple of times, in fact. Yeah, I mean, obviously that there's a lot of uncertainty there in the sort of vegetation models that Corey would know far better than I would. Yeah, I mean, actually, I have a question for him specifically about adaptation, I suppose, which is what about irrigation, which I don't think you mentioned as a form of adaptation. Yeah, that's it.
A question to Corey, right? Yeah.
Yeah, I can quickly answer the adaptation about irrigation, and then I have some other points on the question that was asked. Irrigation's good. It can be expanded in some places. It can't necessarily be expanded everywhere. And as an adaptation specifically for compound heat and drought, I think it's limited because there's a lot of groundwater irrigation that exists in the world, but I think the majority is surface water sources, which would then be limited in exactly the same time as the heat extreme. So as a traditional kind of strategy for dealing with hot periods, increasing drought, heat combinations pose a risk there. Also, some aquifers are becoming stressed, and more will likely become stressed as replenishment rates decline in a warming climate, and as there's more, social pressure on those aquifers. So definitely useful, but I think serious limitations, and those limitations are inherent to compound hazard kind of thinking. I want to say something about models. I guess I'm kind of the person here de facto defending models to a largest extent. But I mean, I agree with all of the hesitancies, but I will say, climate models, Earth system models, general circulation models have always been flawed and have always been biased, and they've been around for more generations than any of the models that we're talking about today. But those models have become an essential policy tool, right? They're still largely ignored. Like, we're not on the right scenario. We're not on the path we need to be on, but we are moving there, and the consensus has changed. And I think the consensus has changed partly because climate models have been a tool to help think through, not necessarily to tell us the future, but to help think through things like a carbon budget, right? I mean, a carbon budget's as simple as saying you need to stop emitting if you want to solve the climate crisis. But to actually quantify that budget, it helps to have those climate models, which you can quantify a carbon budget, which gives you your emissions, caps the point in time at which you need to be net zero, and to quantify the uncertainty in it. So it comes down to the old adage that all models are wrong, but some models are useful, right? And I think it's not the model that's useful, right? It's the application of it. And I think that I appreciate this conversation because I think we understand the limitations of the models, and we also understand that ultimately it's up to our ability to make them useful, not for the models themselves to be made useful.
Yeah, and I would maybe add, basically agreeing with both Peter and Corey, that in the end, it's sorry, I forgot what I wanted to say. I was writing, I was typing answers. I wanted to say that the models are useful to answer what-if questions, basically adding to what Corey and Peter said. And from my systemic risk background, we always say that ignoring the systemic risk factors really underestimates the risk. And a lot of the models are not able to actively model systemic risk and include all of those characteristics. And in general, you would underestimate risks by ignoring systemic risk.
Thanks to all. There is a question in the chat towards Francisca, but I think I want to extend it to all of you. So the question is, from your research, what are the actions to reduce systemic risk that you think people wouldn't have thought otherwise? So we'll start off with Francisca, but I want both of you to think a bit of this question, what are the things that we can do about it that maybe aren't so, clear from before you did the research? And yeah, Francisca, if you want to go ahead.
Yeah, that was also a really interesting question. And basically, I was involved in several global risk assessment reports, GAR, by the UNDRR, 2019 and 2022. And they also had a risk report about drought specifically. And that was very interesting because scientists interacted with policymakers around the globe. We had a lot of debates and discussions. And I think sometimes in academia, we we ignore, we were not aware that reality is slower and more complex than our models. And it's easy to model systemic risk conceptually or in a public academic publications, but in reality, the problems are often that departments work in silos, that the health ministry doesn't talk to the environmental ministry, and talking to those policymakers within that IGAR processes was really, really helpful to understand that in general, telling people or making policymakers aware of the interactions between different fields and different sectors, and maybe helping them to point out within their own governments that the interaction is more important. Synergies and trade-offs have to be examined specifically. I think that is already very helpful and was very helpful within that process. Yeah.
Thanks. Peter, Corey, Peter, go ahead.
Yeah. So I think the point I would like to make is that there's sometimes a kind of a connection made between kind of complexity and globalization of the food system and sort of a vulnerability or a lack of resilience of that system. Sort of axiomatically, you know, long supply chains, complexity leads to fragility, and actually I think the opposite. And the modeling to some extent suggests the opposite as well, in that, you know, having lots of links and lots of complexity and lots of diversity in terms of how that system is structured leads to a resilience. It leads to a flexibility, because, you know, one link can change or break or something like that, and then the system, yes, its system moves and shifts, but it has a sort of smaller. It can, you know, it has a lot of sort of adaptive capacity to absorb that, and it can spread that, whatever has happened, it can spread that across a bigger system. But, you know, both in terms of production and consumption and everything in the middle. So yeah, I think that complexity breeds resilience rather than vulnerability, and that would be a message I would like to stress, I suppose.
Amazing. It's also highlighting the cascading effects also between the moving parts, right. How important it is to look at the whole system together, right? Corey, do you want to add something here?
Yeah, I totally agree. I mean, I think if you use statistical models, it seems like the complexity of the food system in general increases global food security. And I mean, you can see that in ecosystems too. Simplification of ecosystems is not good for their stability. Not the same thing, but there's an analogy there. I just wonder to what extent, if the understanding of how risk is spread and reduced overall in that system in a historical climate is taken for granted to be the way that that system should be built, that it can actually be stressed and amplify food security risks in specific places. And I mean, one thing here is while I'm convinced that food trade and complicated food system networks across the globe overall increase food security, I think that doesn't work in import-dependent places. And there's a connection between import dependence and this kind of international consensus that countries should feel comfortable importing most of their food and not subsidize local agriculture, which is seen as economically inefficient. I think there needs to be a counterbalance to that in some places, particularly North Africa, Middle East, and parts of sub-Saharan Africa.
Thanks. We're almost at or already a little bit over our time, and I really want to ask you one last thing. So I think Peter mentioned something about, you know, like especially how the system absorbs this type of shocks, and, you know, if something happened in a given year, then maybe the system, you know, can adapt to it to a point. But I'm guessing this absorption power, this resilience really decrease if the system is shocked year after year after year. So my question to you will be like, do you think, you know, our current models, knowledge is even suited to sort of assess this risk of like year after year shocks? And if yes, are there any, you know, efforts to do something like this that you know of, or like that you would like to see? Peter, you're already shaking your head so much, so I'm gonna start with you.
I think it depends what the shock is, you know, because if it's a shock that occurs, if it's the same shock, you know, if it's this, or it has a similar effect, if it reduces yield by 10% and it's the same each year, then it's not really a shock. Or, I mean, okay, it could be a shock, but, you know, the system adapts to that, and it becomes just part of the you know, and it may be affecting this country or this region or this crop, and then it's affecting a different crop. But it becomes part of the system, if you like, if it's happening regularly. So yeah, it depends what it is. Just because it's happening multiple times doesn't necessarily make it worse. I mean, it could, and I think a little bit responding to the previous conversation, is the thing that really causes trouble quite quickly is a breakdown in international trade, particularly for countries that are very dependent on international trade. That's a link that's very difficult for the system to adapt to, and that is why we do, countries do need some level of self-sufficiency and do need, diversity and sort of moderation in that dependency as well.
Thanks. Do you, Corey or Francisca, want to add something to this? Francisca, do you want to go first?
No, I think I don't have anything to add.
Great. Then if Corey, if you want to add anything, you seem like you're thinking.
I had something to say, but I can't remember what it was also.
Well, I think this marks that we've been at it for a while, so maybe it's time to stop, but I really appreciate it.
I mean, I think the thing about the shocks accumulating over time is, to an extent, the system can respond, but if we're looking at long-term changes towards a stressful situation, I'm worried whether the trade with storage and local policies works indefinitely, and that the adaptation can happen in a coordinated and effective way amid this poly crisis. Yeah.
It depends, right?
Really depends.
Yeah. And I have to go and pick up my son from nursery, who's already upset that I'm late.
Well, thank you all so much for staying a little few minutes more. I think it was really, really insightful to have you all today. And I thank you also to all the participants that attended. Yeah, I hope this was useful for you as well. And again, thanks to all of you and to the WCRP too for hosting us. So
Thanks.
Thanks for the invite.
Bye.
Yeah, thanks, everyone.
Thank you all. Have a nice evening. Bye-bye.